Hello, everyone. Thank you, Rahul and Mina, for inviting me here. So this talk, I will give a short, quick survey on some simple techniques that can be applied to design satisfiability algorithms and also prove average case lower bounds for formulas. Okay. So as beginning, I will have a short review on the traditional techniques on proving formula size lower bounds, namely the shrinkage and the random restrictions. And then we'll see that this property can be generalized to shrinkage with high probability. And this concentrated shrinkage implies formula set algorithms and also average case lower bounds. And at the end, I will have a list of applications of almost the same technique, but over different other kinds of circuit model. Okay. So here we are concerned with boolean formulas over De Morgan basis. So you can think of formula as a binary tree where internal nodes are labeled by AND and OR gates, and leaves are labeled by literals. The size is the number of leaves. Okay. So formula size lower bound question is is like this. Given a hard function, what is the smallest formula size that computes that hard function? For example, this parity. So for the upper bound, we know that parity is computable by quadratic size De Morgan formulas. But what is the smallest size for computing parity? Okay. It turns out that the lower bound matches with the upper bound. But how can prove such kinds of lower bounds result? Subbotovskaya introduced this random restriction approach that can help prove formula size lower bound. She essentially proved this n to 1.5 size lower bound. Although this is not optimal, it can be improved to n to 2. But let's have a look at her techniques. Okay. So the idea is simple. She basically shows that a Boolean formula size shrinks non-trivially under random restrictions. There are many different ways to define random restrictions. Here, let's consider a very simple one. So I want to do this restriction step by step. At each step, I pick a variable randomly, okay, and then randomly assign that variable to be either 0 or 1. And then I do this one by one variable at a time. Along the process, I want to substitute the constants into the formula and also simplify the formula. Now let's see how the formula size reduces. Okay. Well, here is a very simple example. We have this formula of size 5 over 3 variables x, y, z. Now suppose at the first step I choose this variable y and randomly assign 0, 1 and try to simplify it. So there are some simple simplification rules. The rules to eliminate the constants are trivial. We also need these kinds of one-literal rules. Okay, so let's look at this picture. So suppose this AND gate is fed by a literal x and then a subformula g. Okay, so we want to make sure that this x doesn't appear in this subformula g. Because if it appears here, we can apply such equivalent rules to eliminate x from the sibling. Okay, so we need this rule because after we do such kinds of simplification, we are guaranteed that, we are guaranteed x doesn't appear in the sibling. So that means in the next step of restriction, suppose we restrict this literal x. Now, suppose we assign x to be 0, then at least we can eliminate 2 nodes from this tree structure. And if we assign x to be 1, we can eliminate at least 1 node from this tree. So on average, whenever we restrict 1 leaf node, we can reduce 1.5 nodes from this tree structure. Okay. So suppose we are picking a variable. Suppose we start with a formula of size s over n variables, and we pick a variable randomly to restrict. Now the formula size in expectation is going to reduce to s minus 1.5 times the average frequency of each variable. And then this actually goes down by a factor of 1 minus 1 over n to the power 1.5. So that's one step. Now suppose we do this step for n minus pn variables. Okay. That means at the end, I want to have a fraction p of the variables left unrestricted. So in this case, the formula size reduces to s times p to 1.5. So this is the expected reduction in formula size. Okay. So this shrinkage under restriction property directly implies lower bounds for parity. Okay. Why is that? So suppose we have a parity on n variable. Suppose we have a formula computing parity on n variable of size s. Now we can fix n minus 1 variables, and then from the shrinkage property, we know that the size is going to reduce the s times 1 over n to 1.5. So my fraction p here is 1 over n. Now, since this formula computes parity, it must depend on the remaining variable, so it has size at least 1. So that directly gives size s is larger than n to 1.5. Okay. So this is the lower bound proved based on shrinkage property. Okay. Now it turns out this shrinkage was at 1.5 thing is usually called shrinkage exponent. So that shrinkage exponent can be improved. Okay. So suppose we start with formula size s and we restrict the formula up to a fraction p with variables left. Okay. Now let's say, let's let this s times p to gamma to be the expected size after the restriction. Okay. So what Subbotovskaya showed was that gamma is at least 1.5, that, as we have seen. So this gamma was later improved by Patterson and Zwick to 1.63, and later Hastad proved the optimal result to be 2. Now, from this shrinkage exponent, it directly implies that parity requires formula size and to gamma. Now, using Hastad's optimal result for gamma to be 2, that means parity requires formula size quadratic. So this quadratic lower bound is not the best we have. The best lower bound we have is formula size lower bound we have is given by Angius function. So Angius constructed this function which is hard for formulas of size up to n to gamma plus 1 minus little 1. So using Hastad result, this is almost cubic size, n to q. Okay. So let's have a quick look at Angius construction. So for convenience, we have this function on 2n inputs. We divide the inputs into 2 parts. For the second part, we divide the input into log n blocks. Okay, to compute the function, we would like to compute parity for each block. That will produce log n bits. And then I use that log n bits as an address to locate one position in the first part and output that bit in the first part. Okay. So using the shrinkage property, it can be shown that this function requires almost cubic size De Morgan formulas. And this is the best known formula size lower bound we have for now.
Sorry, is there a similar function, the Andrews function, which also achieves the NQ bound?
Sorry,
For which we know the NQ lower bound formula size?
I don't know. So these results were obtained a long time ago. Now in the next, I want to show that the shrinkage happens not just in expectation, but actually with high probability. And that, well, I want to call it that concentrated shrinkage. Okay. So one simple way to show concentrated shrinkage is to use this kind of graded restriction. So here, instead of using completed random restriction, at each step, I just want to pick the most frequent variable appearing in the formula and restrict it randomly. Okay. Now I do the same process after n minus pn steps with high probability. It can be shown that with high probability, the formula size is at most 2 times this s times p to 1.5 is the expected size. So with high probability, the formula size after the restriction is going to be upper bounded by 2 times the expectation. Okay. So one can also think of this restriction process as a process of building up a decision tree, where at each level of the decision tree, I pick the most frequent variable and build 2 branches, and build this up to level n minus pn. Now, if you think of the restricted formula at the bottom of this decision tree, now most of the restricted formulas are going to have very small size, bounded by this upper bound, and very few of them will have larger size. So this kind of property was shown by Ruiwen, and he used this result to give satisfiability algorithm for Boolean formulas, as we will see soon. Okay. So how can we prove this concentrated shrinkage property? So it's actually quite simple. So we can think of this process of generating formulas step by step. Okay. So let's say this F1 is obtained from F0 by restricting the most frequent variable appearing at F0. Okay. Now each formula in the next step essentially depends on the formula in the previous step. And for each formula, we measure its size using S. Okay. So essentially, we can define a supermartingale process based on the size of these formulas. Well, not exactly on the size, but essentially on the logarithmic of the size. And then we want to show that at the end, the final size is concentrated around its expectation. And this concentration can be shown using Azoma's inequality. Okay. So after we get this concentration, let's see how to use this concentrated shrinkage to get satisfiability algorithms. Okay. So as I was saying, so the algorithm essentially builds up this decision tree up to level n minus pn. Okay. Now suppose we start with formula size to be Cn, and then we take this p to be a very tiny fraction. So 1 over 16c squared. Okay. Using that concentrated shrinkage, we can see that with high probability, the formula size after n minus pn steps is going to shrink to be at most half of pn. Okay, so at this level n minus pn, we have only pn variables left, but the formula size shrinks to be half of pn. That means for the shrinked small formulas, half of pn variables actually don't appear in those variables. Okay. Now, to get sharp set algorithms, for those small formulas, we can use brute force search. We can get savings there because half of the remaining variables don't appear in the restricted formulas. And for the tiny fraction of formulas which doesn't shrink this much, we can also use brute force search because there are only a tiny fraction of them. We won't lose much there. Okay, so the final algorithm is like this. We do this graded restriction up to level n minus pn, and then for each restricted formula, we can use brute force search to count the number of satisfying assignments. So it's a very simple algorithm. Okay, so the concentrated shrinkage essentially helps us to bound this running time. Okay. So the running time can be shown to be 2 to n minus delta n, where this delta is in the order of omega 1 over c squared. So suppose c is constant, then we get a constant saving delta here. Okay. So this algorithm works for this c to be, if c is less than quadratic n, then this algorithm is non-trivial. But it doesn't work for c to be larger than sorry, if C is less than root n, this algorithm is non-trivial, but it doesn't work for C to be larger than root n. Okay? But a simple generalization of the algorithm can work for size up to n to 2.49. It's almost n to 2.5. Okay? So for here, we can use memoization technique to count the satisfiability of those small shrinked formulas. Okay, so the reason is that, okay, let's think of the same process, but I want to choose P to be n epsilon over n, where epsilon is a constant less than 1. So that means I want to do this restriction process until there are sublinear number of variables left. Okay, so the whole tree has exponentially many branches, 2 to n minus pn branches. That's large number of branches. But the number of sublinear size formulas is sub-exponential. So the total number of small formulas is much smaller than the total number of branches. So that means I can somehow pre-compute the satisfiability of small formulas and store those results in a lookup table. And then when I go over the bottom level of this tree, I can use my lookup table to save some time. Okay? So this gives the total running time 2 to n minus n over omega 1. So this is still non-trivial comparing with brute force search. Now this algorithm essentially works for any concentrated shrinkage exponent gamma. So while in the previous slides we showed the concentrated shrinkage for gamma to be 1.5, but essentially it can actually be shown, the concentrated shrinkage can actually be shown for gamma to be 2, but using a different process of restrictions. So there are some improvements just based on improving this concentrated shrinkage exponent gamma. So in this first work here, with Valentin Kamenetz and Nitin, we showed that using greedy restrictions, the shrinkage exponent 1.63 derived by Patterson-Zwick actually hold with high probability. And then the same algorithm works for formulas of size n to 2.63. Okay? So in a different work by Komagutsky, Rez, and Tao, they use a different process of random restrictions and show concentrated shrinkage for shrinkage exponent gamma to be 2. But over there, they don't use greedy restrictions. They rely on certain kinds of random restriction. So that gives randomized algorithm. Okay. So these are the best known non-trivial set algorithms for Boolean formulas. So that means for deterministic algorithm, we can handle size up to n to 2.5. For randomized algorithm, we can handle size almost n cubed. Now, one obvious open question is, can we have non-trivial set algorithms solving larger size formulas? Okay. Another open question is that since here, for such algorithm, we use memoization. That means we use exponential space to store the lookup table. Now, is there any polynomial space algorithm can solve the same problem? Okay. Now, another open question is that can we de-randomize this restriction defined by this KRT paper? Okay, so this shows concentrated shrinkage can be used to design satisfiability algorithms. On the other hand, concentrated shrinkage can be used to prove average hardness. Okay. So in the decision tree process, we have constructed. It essentially shows that a De Morgan formula of size, let's say Cn, has an equivalent decision tree of size 2 to n minus delta n. Okay, so that directly implies that De Morgan formulas of size Cn cannot have a correlation larger than this. Okay, sorry, let me say it again. So De Morgan formulas of linear size cannot have correlation, have exponentially small correlation with parity. Okay. So here I'm defining the correlation of two functions like this. So given two Boolean functions f and g, the correlation is the fraction of inputs where the two functions agree with each other minus the fraction of inputs where they disagree. Okay. So this means that linear size De Morgan formula is quite weak. It cannot approximate parity very well. So this gives an average case hardness result. But this average case hardness can be improved because we know that the worst case lower bound for De Morgan formula is cubic size. Okay. So in the work by Subbotovskaya, Rez, and Tao, they essentially proved average case hardness lower bounds for cubic size, almost cubic size De Morgan formulas. Okay. So here is the statement of their result. So they basically constructed a family of functions, Fn. Actually, these functions are computable in polynomial time. So this shows that these functions, they have exponentially small correlation with almost cubic size De Morgan formulas. Okay. So they are.
I think it might have been obvious, but I missed it. What was the? Why do you get the? I mean, you get the small correlation. Why is that enough? Is that obvious? You show the small correlation with the De Morgan formulas. How does that give you a...
So an equivalent statement is that De Morgan formulas of size n to 2.99 cannot compute this function correctly on larger than half plus this exponentially small fraction with inputs. So there are two ingredients in their proof. One is that they prove concentrated shrinkage for gamma almost 2. Okay. So again, here they use, it's like a hybrid of greedy and random restrictions to get this shrinkage exponent. Another ingredient is that they generalize ng with hard function to the average case. Well, it's actually pretty complicated for their generalization, but at a higher level, the picture looks like this. So again, suppose we have this function on 2n inputs. So for the second input, we use extractor to extract a fraction of base from the second parts. Okay? And then for the extracted random base, we use it to identify a position in the first part of the input. But for the first part of the input, in order to get average case hardness, we use error correcting code to somehow expand the first part to be exponentially long. So for the second part of input, we want to use the extractor because this restriction, the restriction where they prove concentrated shrinkage is not a random restriction. There are some deterministic choice of the variables. So essentially, we don't know which base are left unrestricted. Okay, short summary. So KRT paper, they derived this average case hardness for De Morgan formulas, and it essentially matches with the worst case hardness for cubic size. Okay. So essentially, we have shown a concentrated shrinkage property for De Morgan formulas. And on the one hand, we use that property to design better than brute force satisfiability algorithm. On the other hand, we use that property to prove, well, for the worst case lower bound, we have expected shrinkage. For the average case lower bound, we need concentrated shrinkage. So this somehow falls under the connections between algorithms and lower bounds, the paradigm. Okay. Now in the following, I want to show some other other applications of the same technique. Okay. So here we consider the model of formulas over 4 binary bases. So here not only we have AND and OR gates, but we also allow parity gates in the formula. Okay. So Sato and Tamaki, they essentially extended Rahul's result to formulas of linear size, but over 4 binary bases. Okay. So this shows that linear size formulas over 4 binary bases have non-trivial set algorithm. On the other hand, such formulas have tiny, exponentially small correlations with affine extractors. So that's the algorithm result and the average case lower bound result. Okay. Now, in the recent work, actually shows that this result can be generalized to formulas over arbitrary finite bases. So you have a formula, the gates in the formula have a finite fin-in, but they can compute arbitrary functions. So for linear size, such kinds of formulas, they also have non-trivial set algorithm and also small correlation bonds with affine extractors. Okay? So underlying the proofs, we still need a concentrated shrinkage property. Another application of the same technique applies to small linear size circuits. Okay. So here, let's first consider this circuits over De Morgan basis of size up to almost 3n. So the same concentrated shrinkage approach can be applied to generalize the so-called gate elimination method, which was used to prove circular lower bound. Okay. So by generalizing gate elimination, we can get satisfiability algorithms running in non-trivial time, and also average case hardness of computing parity using such kinds of circuits over De Morgan basis. Okay. And for circuits over the 4 binary bases, which also allows parity, so for size 2.49n, the same results hold. There are also satisfiability algorithms, and it has exponentially small correlation with affine extractors. Okay. So essentially, such kinds of circuits, almost 3n over De Morgan basis, is similar to De Morgan formulas of De Morgan formulas of quadratic size. And then such kinds of circuits is similar to linear size formulas over the 4 binary bases. Okay. So one open question is that the results we get here, we still have a gap to match with the worst case lower bounds. Because for circuits over De Morgan basis, the worst case lower bound we have is 5n. But here we can only manage to get average case lower bound for size almost 3n. Okay. And for circuits over 4 binary bases, the best known worst case lower bound is 3n. So the average case lower bound we have here is almost 2.5n. Okay. It's an open question whether or not we can improve the result to such larger size. Now again, underlying the proof, we need something similar to concentrated shrinkage. Okay. Another application of the same technique applies to max set, which was shown by Saki, Sato, and Tamaki in a recent paper here. Okay. So they basically give non-trivial time algorithm for sparse instances of max sets. By sparse, I mean there are only linear number of clauses. Okay. So they basically shows that given max k-set instance with Cn clauses, there exist algorithm running in time 2 to n minus delta n for delta to be 1 over c squared k squared. Okay. So this is non-trivial comparing with brute force search. And also this algorithm runs in polynomial space. Okay. And then for max set, we need to replace this k by log n. So here they apply some techniques to reduce the weights of clauses. Okay. So these are the results they showed in their paper. Now actually, in an ongoing work with Rahul, these parameters, we have shown that these parameters can be improved. For example, for max k set, this parameter can be improved to be 1 over ck, removing these quadratics. Okay. And also the same algorithm can be somehow managed to solve max k CSP, but for sparse instances. So this is my final slide. So here I want to have a short summary of the techniques. So the set algorithms we have before are almost a DPIL style. Okay. So somehow we use concentrated shrinkage to bound the number of branches we generate in this DPIL style algorithm. Okay. So sometimes we need to use weight functions instead of the size function to show the shrinkage result. Okay. So the idea there is that, so sometimes it might be hard to show shrinkage for the size of the circuits or formula. But you can define a generalized weight function. The weight is proportional to the size. And it might be easier to show the shrinkage of the weight. And then the shrinkage of the weight function implies the shrinkage with size. And then you can use that to essentially bound the number of branches here. Okay. And finally, these kinds of algorithms can be combined with other techniques like memoization, and also Gaussian elimination and so on. So using these other techniques to solve different families of circuit classes and also circuits with larger size. So that's all of my talks. Thank you very much.
Are there any quick questions?
You mentioned affine extractors and correlation with affine. What is an affine extractor? Maybe you said it and I didn't.
Well, I didn't say that. So,
okay. So what? Okay, if it's too complicated, let's take it offline.
Yeah. So for the Boolean cube, if you have a linear subspace of certain dimension, a affine extractor is a function that can produce randomness from that linear space.
Let's take it off.
It's not complicated. Just
it's okay. It's okay. Thanks.
All right. Well, let's thank you again.
Thank you very much.